Hello friends, welcome to another tutorial in electromagnetics and antennas series. In this tutorial I'll talk about scalar magnetic potential, and I'll continue the talk to vector magnetic potential in the next video. It's important to understand scalar magnetic potential and its limiting case to appreciate a vector magnetic potential and its usage in magnetostatics. So let's get straight into it. The first key point is that it is denoted by Vm. Now the reason why magnetic vector potential is denoted as V with a subscript m is that electric potential or the voltage is denoted by V. So it's convenient to denote scalar magnetic potential as Vm. And the second key point that you need to remember is that the E vector, which is electric field intensity, and electric potential are related as E vector is equal to negative gradient of V. Now that has already been studied in Laplace equation, Poisson's equation, etc. So you could refer to those videos for a greater detail of this equation, but this is a well-known fact in electrostatics. Now based upon this equation and based upon this analogy, we can simply replace electric field intensity with magnetic field intensity and electric potential with magnetic potential here. So what we get is H vector to be equivalent to negative gradient of scalar magnetic potential. And the other definition of H stems from the fact that curl of H is equivalent to J vector, which is current density. Now this is taken from Ampere's law, and this is, by the way, Maxwell's fourth equation as well. And using two important corollaries for vectors, the first one being the curl of gradient of a scalar is 0. So I repeat this statement: this is curl of gradient of a scalar is always 0, and divergence of curl of a vector is also 0. So you need to remember these two important corollaries because we are going to use them in a bit. So what you can do is you can substitute the value of H, this value of H, in this equation on the left hand side. So putting the value of H from 1 in the left hand side of 2, we get curl of H to be equivalent to curl of minus gradient of Vm, and from this corollary we know that this entire thing will vanish away, and this will give me 0. So what does that implies? It implies that J must be 0. So very important conclusion that comes out is that the scalar magnetic potential Vm is only defined in the region where J is 0. From the above discussion we know that this will happen only when J becomes 0. So if you put this value of H in the Maxwell's fourth equation or the Ampere's law, that will hold true if J is 0. So very important definition for scalar magnetic potential, that Vm is only defined in the region where J is 0, and H becomes negative gradient of Vm, and it's holding true only for J is equal to 0. So that's the limiting case that I was discussing in the beginning of the tutorial. So you need to remember this limiting case of H to be equivalent to negative gradient of scalar magnetic potential, and that's how you basically define it. And next, there are some important discussions that we need to see. We need to investigate the scalar vector potential for Laplacian equation. So how do we do that? We'll investigate that Vm that we are just discussing. If we were to take the Laplacian of Vm, what's the value of that? So how can we do that? We know that divergence of B is 0. This is taken from Maxwell's second equation because monopoles do not exist, so divergence of magnetic flux density is 0, and B is mu naught h, so I substitute B as mu naught h. Instead of h, I just put the value negative gradient of Vm, which we just established that h is negative gradient of Vm if j is 0, of course. So that gives me Laplacian Vm to be 0. So this is the Laplace equation for Vm, and it only holds true for j is equal to 0. So another final definition of Vm, which is the scalar potential, can be obtained as analogy from electric potential. We know that electric potential is defined as E dot dl, so H dot dl will define the magnetic potential in scalar terms, and the units of H are ampere per meter, dl's unit are m meter, so Vm, the scalar magnetic potential, gets the unit ampere. So that's again something that you can commit to your memory. So because scalar magnetic potential has a limiting case, so we'll need to discuss a case where we need to define a vector now where that limiting case is not there, even in the presence of j. How can magnetic vector potential be defined? And that is a well-known vector A, which is known as vector magnetic potential, and we are going to define that, and we are going to study that. We are going to derive the formula for A in the next video. I hope you've understood the limitation of scalar magnetic potential, its limiting case, and now that you have done so, you'll be able to understand A in a better way. So that's about it for today's tutorial. I hope you liked it. If you did, give it a thumbs up, consider subscribing, share the video, and comment if you wish some more videos of different types in EMFT. I'll see you around in the next video to come. Take care, stay home, take good care of your health. Bye bye.